things here. So why are we excited? Why am I excited? What developed my excitement to begin with were our early studies with tDCS that, through luck and a bit of experience before that, turned out to be very successful. And I talked about this last year, so I'll speed through this given the time constraints and so on. The basic thing that we were trying to do was to train people to identify objects that were hidden in complex pictures. So this is one of those pictures. I showed it last year. Anyone who saw my previous talk, can you put up your hand if you see the thread? Are there people who've seen this before who don't remember where the thread is? 1, 2, 3. Okay, well, 4. That's maybe an example of single trial learning, this. And I suspect that single trial learning of threats was an evolutionarily mediated cognitive skill that we have. And maybe that's where single trial learning comes from. You get one shot, and if you miss it, you're gone. But in this case, that's the indication that there might be a threat. In this case, is the shadow of a sniper on the roof line above you. So there were a series of images like this. People, through trial and error, learned to identify these threats. And then we started out with an imaging study. And we looked at the progression of responses, both with fMRI and with MEG, as people learned to do this task. And we found a number of brain regions that altered their pattern of activity as people's performance improved on this task. And a number of these areas, like the right middle frontal gyrus, right inferior parietal lobule, and a few other areas, were accessible to tDCS. So then, in the next stage of this experiment, in a new group of subjects, we brought people in, targeted these areas, and had them do the same learning task. And we looked at the effects of tDCS on the speed of learning in terms of the improvement in performance over repeated trials. And we found a really big effect for anodal stimulation of either F10, so right inferior frontal gyrus, or P4, right parietal cortex, relative to the contralateral arm for the cathode. Both improved performance quite a bit. And we replicated a number of times, and each time there was almost a doubling of learning with tDCS. It was a little bit larger for right inferior frontal than right parietal. We also saw an effect on the right side of this image. The green bar is cathodal stimulation of temporal cortex, also seemed to enhance learning. And in the end, comparing our results to our bold fMRI data suggested that areas that enhance their activity with learning, we could improve learning using anodal tDCS. Areas that decrease their activity, we could improve learning with cathodal tDCS, and vice versa. So cathodal over an area that increased would suppress learning, anodal over an area that decreased also suppressed learning. So the imaging data actually did a really good job of predicting the effects of tDCS and giving us a guide of where to apply tDCS. And our early successes involved a lot of things that these effects replicated. There was a dose-response effect. There was an effect of electrode position. There was no effect of experimental blinding. We were worried that somehow we were giving cues to our subjects. That didn't happen. Artifacts didn't matter. Skin stimulation didn't seem to have an effect, except that the more stimulation people reported, the more poorly they did. So it was actually the opposite direction of an effect that you expect to see from full tDCS versus sham. The benefits lasted at least 24 hours. I suspect a lot longer, but we haven't done studies beyond 24 hours yet. There are cognitive and neurophysiological effects that we found that seem to explain this. There's an increase in glutamate, glutamine under the electrode, but not in the contralateral hemisphere. There's effects on attention as well. We're also seeing that those glutamate effects correlate with changes to functional network connectivity. So through a series of studies and analyses, we're starting to put together a story of how tDCS is allowing people to increase their learning. Now, so we had all this. I'm a believer. tDCS can have a big effect on behavior. Not always, of course, but in our hands it did. What can we use this for? And as I mentioned last year, one of my children got really sick, and it made me look very hard at the state of medicine in this country. And through bad luck, mostly, we just got involved in the worst of it. The treatment was wrong. It made him worse instead of better. And instead of taking responsibility, the doctors that were treating him called him crazy and sent him to a psychiatrist on the same drugs that were giving him the problems. Eventually, we figured it out. But there's so many problems with healthcare today. 100 million people in chronic pain, a lot of people with a diagnosable mental disorder, very few of them really treated to complete health, although many do get better. It's not that it's a complete failure, but there's a lot of problems. And I think part of that is an overdependence on pharmaceuticals as a mode of treatment. 40,000 people a year die of drug overdose. A lot of those people are dying from treatments for pain, using opiates. And opiates is effective in the short term, but in long term can actually cause pain, weirdly, and ultimately cause death. If people get dependent, their dose gets too high and they die. A lot of side effects from drugs, and it's all very costly. So we need better solutions, and I think that tDCS is one example of neurostimulation that could be very beneficial to us in terms of treating a lot of these disorders that currently have no good treatments, or the treatments have side effects that are as dangerous as the original disorder. So we've started to expand our research to look at a number of different potential applications of tDCS. The study you just heard about, we have also funding from IARPA to use tDCS along with mindfulness and games to enhance fluid intelligence. Like the Illinois group, our results were decent, but not as strong as we'd hoped for. And this is one aspect of neurostimulation that we have to consider. There's the effect on treatment, but what about a day, a week, a month later? How can we generate long-term effects? And there are some examples of that, but we really need more, I think. You don't want to have to walk around all day with an electrode on your head. It's not going to work. We need to work out how to use these technologies to produce longer-term benefits where they're needed. We're using it for smoking cessation, having some luck there in our early studies. Helping people with the history of fetal alcohol syndrome. Brian Kaufman did that for his dissertation and found that it can enhance some forms of executive function and behavioral inhibition. Alcoholism prevention. We started out doing a series of pilot studies, and in one of those cells, using the same protocol we used for that was most effective in that learning study that I described first. People who are drinking quite a bit stop cold, and it's really impressive. So we're following that up with a larger study to see if those effects hold in a larger group of subjects. And we have a just-in-time from NIH for a smoking prevention study using similar methods. Using other protocols aside from F10 anode versus contralateral arm cathode. We're trying to replicate Brunellan's work in reducing auditory hallucinations. Our first patients in that study have received a lot of benefit, and they're begging to continue treatment. We haven't considered that, really, that degree of success, but a woman who'd been hallucinating for 20 years stopped cold on their first day of treatment. It's 6 months later, and she still has benefits and is talking about going back to college, which she had to quit when she got sick. So, and it's hugely bright. I mean, this is the only reason that she's not standing here instead of me. She's a very bright woman. So also work in Parkinson's disease and treating traumatic brain injury. So we've had a lot of luck with this F10 versus contralateral arm protocol. A lot of benefits, an interesting variety of benefits. But I wonder how many other protocols are there? And if you look at the numbers, there's actually an astounding number of unique ways to apply tDCS. And if you look at how many electrode locations, the size of the electrodes, the number of electrodes that you can use, current strengths, polarity, anode versus cathode at each site, and how long you stimulate, if you multiply all that together, there's at least 4 million unique protocols. And depending on how finely tuned you do it, up to 8.7 trillion. It's an unreasonable number. There's no way that we can ever examine all these possibilities. What we've done so far is not the tip of the iceberg, it's the snowflake on top of the tip of the iceberg. That's how much we've done so far. And this is how far we have to go to really explore the entire field of possibilities. If you start to include things like alternating current and random noise on top of that, and there's different kinds of random noise, there's white noise, pink noise, and so on. If you add all that up, we're up to 890 quintillion possibilities. It's outrageous. And it's not just electrical stimulation. There's magnetic, there's ultrasound, light interacts with certain enzymes in a way that can modify neural activity. Physical pressure, acupuncture, acupressure. Last time I was here, I think I talked a little bit about work we're doing with mouth guards designed by dentists, which interact with the nervous system in a way that can suppress pain and a lot of motor illness. And for that, again, my son comes up. After I gave a talk here, his pain syndrome led to a motor illness, and about 30% of people that have the pain syndrome, it can turn into a motor illness, probably an effect of drugs again. He was ticking, he was vocalizing, in a lot of trouble. We took him to a dentist. His dentist made him a very small, easy to apply bite guard. It shut down his tics immediately. And I've seen this in a number of people. It works really well. You can modify the nervous system with a bite guard that you put in your mouth. Our nervous systems are much more labial, much more easily modified than I expected. After 25 years in neuroscience, I had no idea that it was that easy to manipulate the nervous system. There's a lot of ways to do it. So I introduced the idea of a hype cycle, and it seems to have made an impact in this community. And maybe we are on the downslope, I don't know. But the point I want to make here is that tDCS is one of a huge variety of potential ways to do this. And what if these hype cycles add up? I don't worry so much about this anymore because this is for one technology trigger. There's really multiple opportunities here for triggers. And I think over time, neurostimulation is going to have more and more of an impact on health, on neuroenhancement, and so on. So again, a quintillion is a huge number. If you stack dollar bills together, it's 3.9 light days worth of dollar bills stacked the short way. It's a huge number, impossible to work through. So the few successes we've had so far, I think, are just a tiny fraction of the total number that are possible. That doesn't mean that anything is possible, but any reasonable change, any reasonable state-dependent change that you can produce in the brain, given so many opportunities to produce changes, might ultimately lead to the thing we're looking for. A way to stop auditory hallucinations and schizophrenia, a way to help people who are addicted recover from that or avoid becoming addicts in the first place, without major side effects, without all the problems that pharmaceuticals present. It's wonderful. What an opportunity for us. I doubt that we've just been lucky so far in the few big effects that we've found. I suspect through all of this, there's a lot more there. But we can't try them all. So what do we need? We need a better understanding of how these things work so that we can predict ahead of time or identify ahead of time what the best protocol is. My guess about the next step here that makes the most sense is that we start to integrate stimulation and imaging even more so than we have. We need it to develop mechanistic theories, exactly how things work. We need it to develop hypotheses of effects, more so than we have. We've begun this process, but we need to continue, and we need to push it farther. We need to use this to be able to optimize protocols, not only for a group, but in an individual, take account of individual differences in brain organization, and use this to develop better models. Now, one point I wanted to make, the work I talked about first, we've had a lot of luck. One situation where tDCS doesn't work very well to enhance learning of that visual learning task is when people are lying down. The effect goes away pretty much. Could it be that their brain is shifting inside their skull in such a way that the current path changes sufficiently to change the effect? Has anyone in this room seen anything like that in any of their protocols? Nobody else. Has anyone tried it? No. Okay. Where do we get our MRIs? What state are they in? They're laying down. This could be huge. I suspect that we need to start, I need to find a sit-up MRI system. There's one in Germany, right? I think at least one. And see what those changes are. If the brain is actually shifting, and if we're doing all our modeling based on our subjects being supine, and all our testing based on subjects sitting up, there could be a problem there. We have a lot of data from my lab showing interesting effects in different circumstances. One of them that we just published this year, we could find that there was a marker in recovering stimulant addicts that predicted the ultimate success of their abstinence. Taking that data long before they relapsed. And those effects are primarily in posterior cingulate cortex, a bit in anterior cingulate, a bit in right insula as well. When I show this data to treatment providers, they don't want to see it. They don't want to know which of their patients are more likely to fail. I don't know why, really. I don't get a good explanation, but this isn't important to them. So what I hoped would turn into something that was beneficial really hasn't. But what it gives us is a target. And looking at imaging studies over the years, there's a huge body of literature now on what's different about the brains of people who are sick. It gives us a lot of information about potential targets for tDCS. This, I think, could be a huge watershed in the treatment of these disorders. We know what's wrong with these brains, we just didn't know what to do about it. Now that we have brain stimulation, potentially this combination could be very powerful. And also as a way to document how tDCS affects the brain. This is part of Brian Kaufman's dissertation work, and he found huge effects on event-related potentials, like Dr. Javits showed us, with tDCS on ERPs, really astoundingly large effects, actually. So what I'm trying to do now is create situations that are going to facilitate the integration of imaging and brain stimulation. Along with Raja Parasurman, we co-edited a special issue of Neuroimage that came out almost exactly a year ago. The other thing I'm doing now is organizing a meeting in Hawaii. You saw the poster before, probably. We have a few people identified to speak who are experts at either stimulation or imaging or both. It'll be in Honolulu, June 12th and 13th, before the Organization for Human Brain Mapping meeting, and I hope you can come. Now, there's a lot of work that needs to be done still. Who's going to pay for this? I was curious, and I haven't seen yet at this meeting, an analysis of how NIH money is being spent in terms of brain stimulation. One thing that I see is a steady increase on grants that include tDCS. and in 2014, 8.6 million about. Looking at the numbers and types of grants, that's going up. There was a little dip in 2011. That was our little recession, turning into a big recession happening. And it was too bad, because right about the time tDCS was taking off, but things have recovered, it looks like, and numbers are back up. There's more larger R01s, and in that other group, that green other group, are a number of Senate grants. Who's funding it? What institutes? Mental health has 7 grants right now funding tDCS work. NINDS 6, Child Health and Human Development 5. And the study sections that seem most willing to fund it are NPACS and MRS. So it's starting to make an impact on the NIH funding community. But we obviously need a lot more. If we have quintillions of studies to do, we're nowhere near that yet. And why should we bother? Again, society, the media has really focused a lot, I think, on neurostimulation as a toy. And it's interesting, it's a social phenomenon, it is. And maybe it's better that people take electricity than take LSD or cocaine or other things like that. Maybe it's better. But it's not the big story. I think the big story is a pressing need for better treatments for brain and mental illness. And that's where this work can go, and that's what I'm excited about. We still need more rigorous testing. We need better idea of safety for long-term use. We've heard that a number of times this week, but it's true. We don't know what happens if you use this every day for a year. We just don't know. And I hope we don't find out the hard way when people buying these over-the-counter systems do that and wind up with really serious problems. So, to wrap up, I want to thank so many people who have been involved in these studies and our funding agencies, and thank you for listening.